Can you see my screen?
Yes, sir.
Yes, sir.
So please let me know when all the people will join. Then I will start.
Sir, I think everyone joined.
Okay, so everybody has Matlab installed?
No, sir.
So please open Matlab. Sorry. Anybody is there who don't have Matlab installed in their system?
Yes, sir. I don't have Matlab in my system.
Okay.
Because I don't have Matlab.
So you did not get that academic license?
Yes, sir. I have a problem. My license is failed. Now it's not open.
Okay, in that case, one thing you can do, you can write down the code, or otherwise one thing you can do, you can right now you can open Matlab in your browser. Do you know how to open Matlab in your browser? If you have already one account, Matlab account with your personal mail ID, in that case you can use that cloud Matlab version.
Yes, sir. Actually, I haven't used it before, but now I'm trying.
Okay, open this. Are you able to see my screen?
Yes, sir. Yes, sir.
So if you have one account opened with your personal mail ID, you can sign in with your account and then use that online Matlab version, Matlab on browser. You can use it. So I'm signing. I'm signing with my KGP ID. Then it will be good for you. Otherwise, you have to write down the code. See, there is Matlab online. You can see, so you can use that thing. open MATLAB online. If you click, it will open in your browser. So in that case, you don't have to install MATLAB in your system. Okay, so I'm. Should I start? Hello.
Yes, sir.
So all the people have joined, right? So there will be one assignment. Okay, so there will be one assignment based on this MATLAB, whatever coding I will do. So I will send one incomplete code. You have to complete that code and submit. Okay. So that is why I am telling either you write down the code or it is better to type in your MATLAB. Or I think it is recorded, so later you can also check. Okay. So you are already know the SIR model. I think ma'am taught you. So see, SIR model is basically used to model any infectious disease, how one infectious disease is getting spread. So you can model using this SIR model.
Rohit, just 1 second. I discussed actually not give them the terminology SIR. Only I have introduced this infectious and recovery with these two compartments. One mathematical modeling which can model the disease dynamics. Okay, so SIR model, if you introduce, you have to tell little bit.
Okay, ma'am. I will tell the basic equation.
Yes, and then only you just help them to learn the MATLAB coding.
Okay. Okay, so basically the three here we are working with three variables. One is S, one is I, and one is R. You can call it state variables. So basically, what I means, I. Okay, so I means the number of infected people. So these we can also act as a also use it as a proportional. So later when I will code, you can understand what is meant by proportional and what is meant if actual number, because we don't have the actual data. So we can model it. So we assume that the actual number of population is 1. So we use it using the proportional notation here. So suppose so this is I means the number, so N, capital N. Okay. So capital N is the total number of population. Among them, I is the number of infected population. So we are interested to study how the infected population is getting increased or decreased. So here it is increased because it is spreading the disease. So this is the basic equation, that is di dt. So this is di dt means you can see it is the rate. So derivative as a rate measure. So it proportional with I. So as if the more people are infected, so it is the high chance that the rate of growth of infection getting infected is more. So A is a proportionality constant here. So this is the basic model. So which we will call I model. But later we will introduce this S variable. So okay, I think here it will be clear. So basically, first we will consider that N is the total number of population. So we assume as N is 1, just because of the simplicity of our calculation, because we do not have the actual data or actual number of population. So among them, S is the number of susceptible population. So susceptible means those people who are they are having chances of getting the infection. So these people are called susceptible. So among these susceptible people, some people maybe get infected, or they should get infected, I think. So this number we will denote it as I. So and what is R? R means the number of recovered people. So among I, some people will be recovered because they will develop their immunity. So they will recover from R. So in this in this diagram you can see. So suppose S is the number of susceptible people. So among them, few people are getting infected. So susceptible means they are having high chance of getting infected, but not all the susceptible people are getting infected. It's a proportional. Some proportion of susceptible people will getting infected. So that proportion we can this is another compartment. So these we can say as a compartment. So this is one compartment, that is susceptible compartment. It is another compartment. It is the compartment of infectious people. So those who are getting infected. So we can introduce it by I. And from infectious people, now what happened? Somebody got infected. So after recovery, he will develop immunity into his body, like in the COVID cases. So few people will be getting, so we will call it recovered, or we will call it removed, because these people will be removed. There is two basic assumption on which we are working. First assumption is those infected stay infected. That is this assumption we will study only for the SI model. So when you introduce R, this will not be valid. Okay, so first we will study about SI model, but okay, so we will focus on this thing, that is DIDT. DIDT is rate of change of getting infection. Okay, so getting infected. So DIDT as a simple I model, DIDT should be proportional with I, and A is the proportionality constant. But if we think at a deeper level, then if we consider S also, so we will consider here that nobody will getting recovered. So only we will consider here S and I. So this DIDT will be proportional with the multiplication of I and S. So A is the proportionality constant, and I plus S equal to 1. So 1, we just assume that 1 is the total number of population. So here we will calculate this proportionality, not the exact number. So we will get this kind of graph if we plot I versus T. If we solve this differential equation, so we will solve this differential equation in Matlab, and if we plot it, so we will get this diagram, that is I versus T. So as the time will progress, so see, first the number of infected people will be less. So number of infected people will be less, and slowly there will be an exponential growth. So can anybody tell that what is the what is the solution of this simple equation, DIDT is equal to A into I? Can anybody tell?
I equals to I naught e power
Yeah.
at,
So basically,
where I naught is the initial.
yeah. Uh, okay, true. So basically, it is the equation for eigenvalue. So I think a few people will know about the eigenvalue. So we don't have to bother about eigenvalue. This is basically, if we solve this equation, the expression of I should be exponential. So that is why it is written here exponential growth. So in the very beginning, if we do not consider S here, then in the very beginning, the curve of I should be like exponential. So remember, here we are not considering S till now. So see, this is the exponential kind of growth. So I will grow as exponential. Okay, but if we consider S also, if we consider S, then what will happen? Then our equation will be changed slightly. So what it will be? It will be di by dt, which is equal to A into I into S. So here di dt varies with only I, but in this equation di dt varies with the product of I into S. So we can substitute S as 1 minus I, because I plus S is equal to 1 is the total population. We can substitute. So if we solve this equation, so this is the second equation. If we solve this equation, then our curve will look like kind of this. So it is this kind of curve is called logistic growth curve. So it is a kind of logistic function, and we can say there is a point of inflection. We can also calculate a point of inflection. How we can calculate? Can anybody tell how to calculate point of inflection of a car? If anybody having idea of calculus. Anybody
Double
know?
derivative of that curve must be 0.
Yeah, sure. So we have to calculate double derivative. So what is point of inflection? Basically, that point in a curve where the curvature of the graph is changing. So here it is exponential, but here it is not exponential. It is little bit changing. It is kind of 1 minus e to the power x kind of graph. Not exactly, just kind of this kind of function. So from at this point the curvature is getting changed. So if we want to calculate this curvature, we have to equate this derivative, and we have to calculate the double derivative. So if we calculate this double derivative, it will be getting a minus 2a into I. It is a simple derivative. If we use derivative, so a is the constant. That's why a come, and a into I square. 2 into I. It will be like that. And if to calculate point of inflection, what we have to do? We have to equate this double derivative with 0. So if we equate, we will get this equation. From that equation, we can get the value of I, and that is equal to half. If anybody is getting confusion in this calculation, you can tell me. So I equal to half is the point of inflection. So here in this curve, if we see, this is the half point and this is the 1. 1 means the full population. So at this point, the curvature of the graph is changing. Okay. So first we will, so this is the little bit theory behind this. So basically this is SI model. This we called SI model. But first we will do I model. Then we will move into SI model. Then we will move into SIR model. So everybody, is anybody having any questions in this theory part? Okay. So start coding. Okay, so here we code I model. So what we are considering, we consider only the infectious people. Everybody is, the basic Matlab command everybody know? Or is there anybody who do not use Matlab before?
Yes, sir. I haven't used before.
Okay, okay, I will try to explain each line, but if you are having any problem, you can tell me. Okay.
Okay, sir.
We divide our code into few compartments. So first we have to check the parameter values. Who having Matlab with them, they can type with me. Then what we have to do? We have to do initialize our parameter. Then what we have to do? We have to build our equation. We will plot our result. So in this code part, we will try to do our coding. So the first part, that is we have to initialize our parameter. Okay. So can you tell anybody what is the parameter for this equation or this equation, for these two equations, what will be our parameter? See, I is a state variable, so I is not parameter. So the parameter is A. A is the parameter, and all the values of parameter will be given to you, so you don't need to worry about. So first A parameter, so we will put it as 1.5. So there is a method, that parameter estimation in statistics, where these parameter values can be estimated using the real data. So right now we don't need to bother about it. So I0 is the initial value. So what we call this? So we call it, percent sign is for commenting. Okay. Call this A parameter as the coefficient. Okay. And its unit will be week 1 by week, or week to the power -1. So what is this I0? This I0, so initially we take it as 10. So this I0 is the initial number of infected people. Then we have to plot it. So we have to make our time axis. So the maximum time, what should be our maximum time? Max also we take it. Is the so these are all our parameters. Okay. Later we will try to change this parameter to see our graphs, what will they look like. Now we have to initialize our vector. So first what we will do, we will make our time axis. So our time axis, to define time axis, we use colon operator. So can anybody explain this code? What this code will do? T equal to 0 colon dt colon t max.
T will range from 0 to T max with the step size of dt.
Yeah. Okay. So this is our time vector. In MATLAB, see, in MATLAB every variable stored as a matrix or vector. You can see here also. So it is stored as a either vector or matrix. In a scalar, see, this is one scalar. So A is a scalar, but it is stored as a vector. So that is why we will call it time vector. We will calculate what is the length of this T function. What it will give? It will give then we will initialize our I vector. So we will create 0 vector first. So initialize our vector as 0. Is same as our time step. And what should be our first value of I vector? Can anybody tell what should be our first value of this I vector? It is
0.
the no, it is the this value I0. So we can make it 0, but actually we make it 10. Okay, we give the value 10. So it is 10. So this is the first value of I vector. Our second part complete. Okay, so we initialize our vectors. So now the most important part has come. This is model equation. So we are so we are going to equation. We are going to use this equation. So we are making Matlab code of this equation. It's a very simple equation. Di dt equals L to I. You can solve it manually also. But when we introduce this SIR model, then the equation will be little bit complicated. So we'll try to see first how to code this small equation. It's a there is a small trick. So what we have to do, if we first if we run here our workspace, and it will run this thing. So it will generate these variables in our workspace. Then we initialize our values. So it will initialize. So here the A value is initialized as 1.5, I0 is 10, and T, you can see what is T? T is basically one vector. Okay, 1 cross 1001 size. So this is T. And NT in the number of steps. So if we see this variable, see, this is the T vector. Okay, vector is a collection of some numbers. So this is T vector. It start as 0 and it will be end at 10. And we divide 0 to 10. This range we divide 0 to 10 as our step size is 0.01. So it is increased in this way, 0.01, 0.02, 0.03. So each gap is 0.01. That is our dt. So our dt is 0.01. Okay. So in this way, we make this t-axis or our t vector. Okay. So now what we have to do? So see, we have to make one for loop and we have to iterate it. This is one sample variable from 1 to nt minus 1. So can anybody tell why I take 1 to nt minus 1? Why I did not take nt? Can anybody tell? See, just now I have shown you this t vector, but the fact is that the first value of t is already, it is initialized. Okay, so that is why we have to see the number of steps here. So for the number of steps, it is nt minus 1. We can also take 0 to nt. We can also take in this way. But in Matlab, everything is initialized at 1. It is not initialized at 0. That is why we are taking 1 to nt minus 1. Then we have to do this equation di. What should be our di? A into now what should be the next value of I? It is it plus 1. How we calculate this it plus 1? Using our derivative rule. So it plus 1 is equal to, first we have to consider the previous value, that is it. Then we have to increase our value at a rate of di into. This is pure derivative equation, if you see. if you calculate this di, what it look like? I of it plus 1, it is just a dummy variable for time axis, okay, time point. So I of it plus 1 minus I of it by dt. This is the form of derivative. So that is equal to di. In this way we calculate this. Okay, so this is how we code this equation. There is also one different style also you can use. This is one style. Now what we will do? We will plot our result. So first we just basically a simple plot we will use. So first x-axis it is t, then y-axis. So just simply do this. And now if we run our equation, what we will do? See, the plot is generated. So as obvious that this equation will give us exponential growth. So this is an exponential curve that we are getting from this. Okay. So now how can we use this? How can we use this thing that is make our plot looks nice? So first we just make it our plot. This will make our plot blue color. Then line width we will take it as 2. Okay. Let's check. See, it will make our plot blue, and line width increase the it will we can clearly visualize. So now axis function, we have to mention the x-axis limit and y-axis limit. Now x-axis limit, so can anybody tell what should be our x-axis limit? If you are having problem in any of the line of code, you can ask me, okay? Otherwise I cannot understand. So our x-axis limit, x-axis we will plot t. So our x-axis limit is 0 to t max. And y-axis limit 0 to I max. So you have initialized this I max here also. Oh, we do not initialize. Okay.
Excuse me, sir.
Yeah.
In model equation, why did we take di into dt?
Yeah. This equation we are
in that Matlab code. That in model equation for loop third line.
This is.
I of I, yes, di into dt.
So see, this is the style of doing this kind of. You can also use different style. What I calculate here, I calculate first the little increment di. Okay. So see here, for each value of t, for each point of t, we are calculating this small increment. Okay. So after that, we just multiply it with dt. So if we rewrite this equation, you can rewrite it. If we take this term here, so I of it plus 1 minus I of it, it will get, and take this dt here, divide by dt is equal to di. So isn't kind of the derivative term? So there will be little bit. You cannot, so you do not compare it with the mathematical calculation. It is the way of writing code. See, for mathematics, it is a continuous function, but in Matlab, it is not a continuous function. We are actually calculate the different values of I for the different values of the t. T here has 101 points. So for each point, we are calculating what should be our value for I, and it is getting accumulated. You get it?
Yes, sir. Yes.
Okay. So this is our axis, and also we will add grid on. We will add also grid y naught and our x level. Our x level is time in weeks. Proportion of into add one title, that is okay. If we run our code, so just put any one arbitrary value. So here we use scientific notation. It's mean 5 into 10 to the power 4. So see, so this will generate our graph. Okay, so this is our first model, that is only I model. So you can see the initially the number of infected people will be less, but as the time will progress, the number of infected people will be more and more, and it will be increase at a exponential rate. Okay. So now what we will do, we will move this thing and we will make one another model, that is SI model. So we'll copy our whole code. So we have to change in this code a little bit to make it our SI model. So this is our SI model. Variables are S and I. These are our state variables. So here we will consider susceptible people and infected people. So A value remains same, and I0 value. So we will make this time I0 as very small, something like 0.001. So we consider that there are very small people are getting infected in the very beginning. So this is our time axis, 10 weeks. This is our DT. Okay. And so it will be our parameters and initialize our vector. So T vector will be as it is. NT is the length of our vector. So number of time points. This I is basically I is the value I0. Here we have to introduce another vector, that is S, which will be equal to zeros and has also the same size as 1 cross NT. So you will create zero vector of S, name it, it is our So now we have to change a little bit in our code. So now what we are going to model, so we are going to model these two equations. One is di dt is equal to a into I into s and I plus s equal to 1. These two equations we are going to use. Okay. So basically here our infection rate depends on the product of infected population and also susceptible population. Both the two variables our infection rate is depending, but in this equation only the number of infected population this rate was depending. So we have to modify our code also little bit. So di for it equal to 1 nt minus 1. So first there is this. S of it. So what should be our S of it? It should be 1 minus I of it. Then our di, so we have to multiply here and rest of the thing will be same. Let's see. So it's not showing anything, but it's okay. This is our graph. So this is basically I graph. We are plotting basically I graph. But if we plot our S graph also, then what will happen? So we make, so right now we can plot our I graph, also our S graph, and also our SI graph. So we use switch case statements. Just like C language. Variable, that is plot choice. Make three case. And then end. So we have also initial we have to make this thing. Okay. This is set parameter, this is vectors, this is model equation, this is plot. So we just copy this code and put it under case 1. So if you press Ctrl plus I, if you select it and press Ctrl plus I, it will be automatically indented. Okay, so you don't need to be indent manually. So first we will plot S value. So here it should be susceptible. This is infected. Let's this one. So it is actually working, but we have to change little bit this time scale. So then we will see the full result. So it is I curve, and finally we should plot the combined plot. So 3 plot we are using this almost the same thing we are using. It is plot of T versus S, it is plot of T versus I, and here we will plot both the curve. So first we will make our infected as R. So it will be it will make our line red. After this we will plot T comma 1 T comma S. So T versus S it will plot, and we will make this as okay, line with these two. Now if we plot this thing, so we have to increase our the curve is generating, okay, but we cannot see as our time axis is limited. So we can increase our time axis as 52. For a whole year we want to see. Vectors must be of same length. So T is okay. So T should be this thing. Oh, we just changed this T max. That is why it was showing like this. But let's change this value to 2.5. This is 1.1. Oh, actually there is, I have not created this S vector here. That is why it is giving the error. So see, now this is giving, but 0.001. A is 1.25, P max is 10, P max is 15, DP is 0.01, it is 0.01, 9 max is 1.5. So this will make it as 10. So now it is giving this result 10. So this is our second equation, and if we run this model, so actually there may be some parameter value we have to change in this way. So if we see I0 parameter value is 0.0001, A value is 1.25. This is some standard value for making this plot. T max is 10. So 10 is the number of weeks, and maximum I max we just reduce it up to 1.1, and DT is 0.01. And we plot it. See, one plot choice one is for only we want to plot. If we want to plot only S variable, it should be 1, or if we want to plot I variable, it should be 2, and if we want to plot S and I both, then we have to make it is 3. So now everything is similar, and here is the plotting. So if we run this, this will make this kind of curve. So this blue line is S versus T, and this red line is basically I versus T. So this is our susceptible graph, and this is our infected graph. Okay. So as we are seeing that first the susceptible people, susceptible means those who are having the probability of getting infected high. So this is our actually initially we initialized as 1. So 1 is our total number of population 1. So here if we see y-axis is up to 0 to 1. So it means that we are calculating. So we just normalize our total population as 1. So we are calculating the proportion. So what is the number of proportion that are getting susceptible? So see, number of susceptible people also getting decreases because the number of infected people getting increases. That is why S is getting decreases. So as more and more people are transforming from S to I. Okay. Okay, so right now this is the last model. that is our susceptible people. So see, this is the susceptible population. So at which rate the number of susceptible people are getting infected, it is the rate is A into I into S. So in this rate, susceptible people are getting converted into infectious people. So from the infectious people, in the rate of B into I, the number of infectious people is getting removed or recovered, or actually they are building immunity among them. So that is why they are recovered and they moves into this S part. So DIDT, what DIDT is measured? DIDT measuring how fast the infections are growing. So it is the measurement of how fast our infectious people are, so people are getting infected. So in this SIR model, little bit the model equation is getting changed. So what we do, so DIDT is equal to A into I into S. So this is the number of this is the number of infectious people are getting infected minus B into I. So what is B into I? See, whatever is input, we have to take it positive, and whatever coming from the compartment, we have to take it as negative. So this is BI. Actually, in this BI rate, the number of infectious people are getting recovered. So we have to negate this BI. Okay, so AIS minus BI. And our total population does not change. So S plus I plus R equal to 1. And DSDT, what should be our DSDT? So see, from DS, this is our S compartment. So from our S compartment, A into I into S are getting infected. So we have to make it negative, because in this rate, susceptible people are getting infected. So it is reducing from this compartment. So DSDT is equal to minus A into I into S. So, and what should be our DRDT? DRDT simply B into I, because in this B into I rate, infectious people are getting recovered. So we will assume once one people getting recovered, he will not be infected again. So we will consider that that person is getting immunity and he will be not infected. So now we will our last model equation. So we will model this equation. So we will copy this code. So now it will be SIR model. So this model is for the spread of disease that is dependent on the state variable S and I. Okay. And here also on logistic growth curve will be generated. So first, what should be our parameters? So I0. So here I0, what we will do, we will make it little bit smaller. So we consider that only few number of people are getting infected at the very beginning. So see this model parameter. So if you change your model parameter value, your graph will be also changed. So and these values will be given. So this is our A. So our B value will be 0.5. We will consider it. So what we call our B value? It should be removal coefficient. Weak to the power -1. Then Tmax, we will plot it throughout the year. So 52 weeks. What should be our Imax? Imax is 1.1, and our DT value remains same. Now choices. Now there will be one. Okay. So 1 is for S, 3 is for R, and 4 is for. So here we will get 4 plot. So basically we're interested in all the plotting. So we want to see how all the variables S, I and R, how these variables are getting changed. So the next part, initialize our vector. So T value will be remain same, NT will be same, I0, S0. Then we have to build one vector, that is R vector, also 0. Or recover. Why we will call it removed? Because we consider that once a person getting immunity, he will be never infected in future. So that is why we just remove that person from our system. I0, okay. Now comes the model equation. So now we are trying to model these three equations, dr dt, ds dt and di dt, and this is another equation, s plus I plus r is equal to 1. Previously, if we do not consider this r, then it will become s plus I is equal to 1. So for it is equal to 1 into nt minus 1, sit is equal to 1 minus it, then it will be r into it. Plus r equal to 1. Then how we will change this di equation? So di equation is a into it into s. We have to introduce this term minus bi, minus b into it. Then we will make this I equation, it is absolutely fine. Then R is equal to B of IT. So you can see from this, dr dt is equal to B into I. So similarly, dr is equal to B into I of IT. And what should be the increment of I? IT should introduce R of IT plus we have to multiply dr into dt. This our model equation is formed. So now what I have to do, case 1 is for S, case 2 is for I. So we have to do 1 is for so we'll change this I to R. So we will make it our color magenta. Everything is okay, and here it is proportional, it is recovered. In title also we have to change this thing as recovered, and here what it should be, and to go next line, then we have to plot T versus R. We will use So it will first plot t versus I with red, then t versus S in blue, then t versus R in magenta. Otherwise everything is remains same. And we have to change this thing. See if we plot it. So our equation as is. If we run it, see. So now you can see the three equations are getting plotted. S, I, and R. These are the three equations. So these three equations, these three differential equations are getting plotted. So we use Matlab code for plotting this equation, and we plot I versus T, then S versus T, and then R versus T, and how it is getting changed. So this is the, so basically why I call it proportion, because basically we are not considering the exact number of figure. So we consider that our total population is 1. So how, so what is this blue line? This blue line is the S variable. So it is basically S versus I. And what is this red line? This red line is the number of infectious people. So those people who are getting infected, so rate of infection is getting plotted. So I versus T. This is a red line, and this curve, that is logistic growth curve. This is the R curve. So R versus T. We can also plot it differently. So if we plot only one, so this is the S curve. If we make our choices here, so we can change these plot choices and we can check our plot. So please do not change these value, otherwise your plot could be cannot be generated in a proper way. So these values are already predefined. So this is our R. Sorry, this is our I curve. So proportion infected versus time. This is our R curve. And finally, if we want to, so this is our SIR model of infectious disease, how our infectious disease like corona is spreading. So you can use some basic mathematical model and you can plot the result. So how it is getting plotted. Okay, so anybody has any doubt? Hello?
No, sir, no doubt, sir.
Okay, so I will give you one small assignment. So I will give you one incomplete code. You have to complete that code, and only a few things. So there is one parameter that is R0, on which we can also incorporate vaccination on kind of this thing. So you just complete this assignment and submit it. Okay. So you submit it within one single M file. You have to submit, and you have to submit all the figure in a separate PDF file. So you can save this figure and import it in a Word file and make it a PDF, and submit one M file and one PDF file. Clear, everybody?
Yes, sir.
Okay. So this is all about. So I will share these notes with you. So can go through this thing, and if anybody having any problem, he can also contact me. Okay.
Sir, can you also share the 4 coding files, same files?
See, I will share, but actually what happened, you have to, so you have to solve those assignment based on these files. So few lines will be omitted, you have to complete it, and just little bit modification you have to do. That is why I'm not sharing coding file right now. After you submit your assignment, I will share all the coding files.
Okay, sir. Yeah.
And also I show you one small example, that is, see, here I use A, B, C, this kind of, so I use this as a parameter. A little bit there is changing. Here it is used as beta, gamma, and delta. Okay, so otherwise everything is remaining same. So a little bit I'm just explaining this thing. After then ma'am, I think ma'am will take your class. So see, what is S? So if anybody having any problem regarding the understanding of this SIR model, he can tell me right now. Because unless you understand the little bit basic of the SIR model, your assignment, I mean, you cannot complete that assignment. Okay, so what is S? S is the susceptibles, those who are getting infection. So S is those population who are having high chances of getting infected. I is the number of infected people. R is the recovered from infection. And these are the 3 model equation. So first, what they are doing, this is beta, gamma, delta. These are the model parameters. So basically, these 3 are the parameters, not N, and these are not the parameters. But we call it also parameter because we have to put some external number to it. That is why. So here is the same graph that is generated. So you can add this ligand part. You can add this in this way. You just have to put this command, ligand equals to SINR. Okay. And this is the function of SIR model. So so I told you that you can also code it in a little bit different style. You can also code. Okay, so it is a little bit different way it is getting coded. So here dt is already multiplied before, and then this is the increment value was calculated. But here I multiplied this dt value along with while I am calculating this increment. Okay, that is the little bit change. Otherwise everything is similar. So okay, thank you everybody for attending the class. I think ma'am will take this.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Welcome.